All right, so we're going to get started then with exponential functions. At the very top, this is kind of going back to 1.2 when we talked about different types of functions. So making sure that you understand the difference between a function of the form f of x equals 2 to the x and then g of x equals x squared. So when you have a constant to a power where the power is the variable, this is exponential, versus if you have a power but the base is the exponent, or the base is the exponent, that makes sense. The base is the variable, and then the exponent is a constant or just a number that is a power function. And when we get into derivatives and integrals, you definitely see power functions more so than exponential unless it's the natural base of e. But the derivative rules for both of these types of functions often get mixed up. Students often want to use the derivative rule for a power function and apply it to exponential. So you might look at this and say, well, yeah, we can recognize the difference, but just make sure you understand that because they're different functions, you work with them differently when we get into the actual calculus part. So in general, an exponential function has the form, we wrote this in 1.2, but f of x equals a to the x, and a is a positive constant. So the first thing I have for us to look at are just some characteristics of the graphs of exponential functions. So I have on here to graph members of the family of functions y equals a to the x for these 4 different values of a, and graph them on the same screen. So I'll graph them on my calculator. You can certainly look up at my screen, but if you want to graph them on your own to see that right in front of you, you can certainly do that as well. And make sure when I'm typing in, for example, 1/4 to the power of x, I should put the 1/4 in parentheses. And I'm just going to do the standard viewing window. So zoom 6. What? Oh, mine's not graphing that fast either. Yeah, the Inspire's just graphed. That's true. One thing that is nice with it graphing this way is it graphs them in the order you put them in. So that's one nice thing. But do yours get labeled right away too? Like it labels yours on the graph? All right. So just looking at these graphs, and you certainly, if you're graphing this on your own calculator, could adjust your window if you'd like to. So the red, or the blue, sorry, that was the first one, that was 1/4 to the x. The red is 1/2 to the x. The black is 2 to the x. The pink was 4 to the x. Let me see these questions that I have on here. What do all of those graphs have in common besides being all exponential? They never hit the y value of 0. So we would say the line line y equals 0, which is the x-axis, is a horizontal asymptote. Move my calculator so I can write this. All right, anything else they all have in common? They all intersect at the same point, which is what? Yes, so they all have a y-intercept of 1. I'm going to write it this way. They all pass through the point 0, 1. My question for this is why? Why do they all pass through 0, 1? Yes. Ben? Yes. So here, any value of a to the power of 0 will be 1. And there isn't any transformations happening that's shifting them. So yes, a combination of those two ideas. Is there anything else they all have in common that you would say? We hit the two main ones I was looking for. Or then for B, do you notice any other relationships that exist? So not necessarily things they have in common, but relationships between the graphs, Sam? Yes. Who heard what Sam said just now? There was a lot of side conversations going on. Sam, can you repeat what you just said? Smaller than 1. Yeah, so we could say for A values that, like you said, are less than 1 but greater than 0, we will be talking a lot about the slopes of the curve, so negative slopes. I'm actually going to put that in parentheses. These would be decreasing functions. It does mean, though, when we get into talking more about slopes, that it does have a negative slope. So we talk about curves having slopes, not just lines having slopes. And then A values that are greater than 1 are increasing functions. Or have positive slopes. And you'll see in calculus, that's a huge idea that if a function is decreasing, we'll talk a lot about the slope of a tangent line, and the slope of the tangent line is negative. For a function that's increasing, the slope of the tangent line is positive. We talk about that idea quite a bit. Any other relationships that you would pick out from these? Okay, so there are two pairs of symmetric curves. Y equals 2 to the x and 1/2 to the x are symmetric. They're just reflected over the y-axis, and then 4 to the x and 1/4 to the x are also reflected. So I'll just put one example, y equals 2 to the x and y equals 1/2 to the x are reflections over the y-axis. Anybody know why that is? Well, it has to do with them being reciprocals, yes. What if I have y equals 1/2 to the x, I could write this. I could flip the base of 1/2 to make it a 2 or 2 over 1. And if I flip the base, what happens to the exponent? It's not a logarithm. That's not the direction I'm going. So it turns negative. I'm talking about algebraic properties. So if I flip the base, usually we make a negative exponent positive, but we could also make it negative. If I take the reciprocal of the base, now the exponent is negative x. And this is really then if 2 to the x, if this is f of x, this then is f of negative x, which is a reflection over the y-axis when we talked about transformation. So that's y, just so you understand the y there. Okay, so I think we hit most of the relationships or similarities that I was looking for. And these we kind of already talked about. I just want to list them out again. So I have 3 different cases if you have y equals a to the x, where a is a positive constant. A could be a number greater than 1. A could actually equal 1. A could be less than 1, but still greater than 0 since it's positive. So if a is greater than 1, you will have an exponential function that is increasing. Okay, so this is just characterizing based on the a value. So the function will be increasing if a is greater than 1. I know we had already talked about that in our relationships above. And then what domain and range do these have? Or does, I guess, these functions that are exponential and are increasing? All real numbers for the domain, so negative to positive infinity. Range? Yeah. Not including 0. Okay. And then case 2, so if y, or I'm sorry, if a is equal to 1, what does that graph look like? Okay, it's a line. It's a horizontal line. So this would be y equals 1 to the x and 1 to any power is itself. So all of your y values are 1. So it's a horizontal line through 1. Okay, so this isn't exponential at all, but I just wanted to clarify it because a is just defined to be a positive constant. 1 is a positive constant, but this is not exponential. This is a constant function. All right, and then for case 3, we said if the a value is between 0 and 1, then it is a decreasing exponential function. And domain and range would be the same as the increasing. Of course, if there were transformations happening to it, the range would change, but the domain would always be all real numbers. And then before we get into a couple of examples, I just have as a review the laws of exponents, and we'll review these quite a bit when we get into derivatives because we'll use them a lot to simplify expressions before we actually find derivatives. So if a and b are positive numbers, x and y are any real numbers, what happens when you multiply powers that have the same base? You can add the exponents. So this would be a to the x plus y. So when you multiply powers, you add their exponents. The one below it, yes, when you have a power raised to another power, that's when you multiply the exponents. That would be a to the xy, a to the x times y. What about 2 when you divide powers with the same base? You subtract, so a to the x minus y. And then if you have a product to a power, like ab all to the x, you have a to the x, b to the x, so you can distribute that exponent to all of the bases. Now, notice that's only if what's inside of the parentheses. This would be true for division as well, if there's a product or quotient inside. If you have something like a plus b to the x, you cannot distribute that. You cannot distribute that and say it's a to the x plus b to the x. So this is a big not equal to this. Okay, so it's only if inside the parentheses you have a product or a quotient. If you have addition or subtraction, it does not apply. You cannot distribute. Okay, so we're going to go through an example that will require your calculator. So example 1 says to compare the exponential function f of x equals 2 to the x and the power function g of x equals x squared. And then it says which function grows more quickly when x is large. I gave a hint to find where the curves intersect. And as we go through this example, I'm actually going to point out some other features you can use on your calculators to help you graph. So this is kind of like a learn about your calculator example as well. So I'm going to go back to my y equals to enter my functions in. I'm just going to clear these and put them in a different place. So I'm going to graph 2 to the x as y1, and then x squared as y2. And I'm just going to start with the standard window. I always start with the standard window, unless I think I showed you if you're graphing a trig function, there's a zoom trig option. That's kind of like my standard window for trig. Okay, as you're getting that grapher, you can look at the my window may not be the best because there seems to be a lot happening here. So when it says to compare them, and I gave a hint to see where they intersect, you might be able to just look at these functions, or you probably are able to look at these functions and say, in the end, which of these two functions is going to have a larger y value? 2 to the x or x squared? Okay, I'm hearing some different answers, so then it's good we're going through this example. Okay, so as we look at this, I see there's one intersection right here, and then it appears there might be another intersection here, something's happening up here maybe. I'm going to change my window slightly. So I'm going to now go to window. I don't need my y min to be as low as it is, but I'm also going to change my x min and max. So I'm going to shift it so that my x-axis is kind of shifted over a little bit. So I might just change my x min to, I don't know, -5 maybe. I'm going to leave my x max at 10 right now. My y min, I'm going to change to, I'll change that to -1, since neither of those two functions goes below 0. My y max, I think I might raise a little bit to 15. I'll try. And you can watch them graph too to see if you can notice how many times they would intersect. And it looks like they intersect 3 times. I'm actually going to go back to my window and change. I don't think I could see my intersection. Change this to 20.
Oh wow, that's very easy to see. It looks like it turns into one line.
Okay, so then so I changed my window. I'll go back and show you. My x min is -5, x max is left at 10, y min I changed to -1, y max is 20. And I can actually see 3 intersections. There's one down here, and then it intersects twice, and one's up here. Once I change it to 20, I could see where that was occurring. And then if I graphed this, if I zoomed out from this, and I might do that later, then you could see they wouldn't intersect again. But if you needed to see, do they intersect more than that, you could definitely change your y max and double check. I would like to find where those intersections occur. So I am going to first find this intersection that's down here. So I'm going to go to second trace for the calc menu, option 5 for intersect. Now here you do need to make sure, because there's more than one intersection, then you do have to make sure that your cursor is really, really close to the intersection you're looking for, because otherwise it'll find a different intersection that you didn't want. And make sure you're using the left and the right arrows to get your cursor moved over. If you hit up or down, it changes the curve you're on. So enter for first curve, enter for second curve, enter for gas, and then it tells you the intersection. So the first intersection happens at approximately negative 0.767. I'm just going to make note of that. So that's approximately where the first intersection occurs. And notice to the left of that intersection, the graph of x squared, all of those y values are greater than the graph of 2 to the x. So from negative infinity up to negative 0.767, x squared is larger. The y values are larger. Then that switches for a short interval, because there's another intersection here. So I'm going to hit second calc or second trace again for calc, option 5 for intersect. Arrow closer to this intersection. Enter for first curve, enter for second, enter for gas. There's another intersection at 2, 4. So at x equals 2, there's another intersection. So from negative 0.767 to 2, now 2 to the x is greater than x squared. And then it switches again. Now, if it's kind of hard for you to see, especially if you don't have a colored screen, it might be hard for you to see what's happening here. I want to show you a feature I haven't showed you. Maybe you've played around with it, and that's called Zoom Box. Many of you tried Zoom Box on your calculators? Okay. So Zoom Box, if you go to Zoom, it's the first option. I'm going to hit enter. Now, what you're going to do is you're going to create a box around the part of the graph you want to zoom in on. So I want from this intersection to approximately where this one is. So I'm going to move my cursor kind of where I want the lower left part of my box to start. So I'm going to hit enter here. And now when I move my cursor, you're going to see a box start to form. Okay, you want to fit the piece of your graph that you'd like to see in that box, because then when I hit enter again, what's in this box is what's going to be in my viewing window. So if I hit enter, now I'm only going to see that part. And again, the blue that's showing on mine, that's 2 to the x, and the red is going to be x squared. So they're very, very close together, but I can see down here, this was 2, 4, the intersection we just found, and then x squared is actually larger when it comes to the y values than 2 to the x until we get here. And now it's a little bit easier to see that intersection since the curves are so close together. So I can do second trace now. I could have done and found that intersection on the previous screen. I just wanted to show you the zoom box feature. You can zoom in if you want to see it more clearly. Enter, enter, enter to find this intersection, which is at 416. And then after that, After the x value 4, they no longer intersect. 2 to the x, then the y values are all larger than x squared. Okay, so how I could answer this question when it says to compare, I really didn't have to find all three. I just wanted to show you as we're looking at these graphs. But I can say for x values greater than 4, f of x equals 2 to the x is larger, or you could say grows more quickly. When you say is larger, grows more quickly, you're talking about the y values, is larger than g of x equals x squared. But notice I'm saying that more specifically than just, well, obviously the exponential function is going to grow more quickly than a power function. But I'm saying after 4, so leading up to 4, they kind of switch back and forth which one is larger. After the x value of 4, 2 to the x is always larger. Okay, so some problems like that might have you kind of play around with your calculator to see what's going on. We do that a lot with different functions, graphing them, really looking at the graphs to see what we can gather from those. Any questions on that one? Okay. The next example, I'm not sure, I think you might have done problems like this in pre-calc. But I mean, I didn't teach you in pre-calc, I can't say that for sure. But dealing with modeling with exponential functions, so coming up with an exponential model. And we will actually do this using calculus later on in the year as well. But anytime we're talking about exponential growth or decay, so this happens a lot with population growth or radioactive decay of elements like it's saying here, then we would use an exponential model. So this example is talking about a half-life. So it says the half-life of strontium-90, so this element is 25 years. This means that half of any given quantity of that element will disintegrate in 25 years. So part A says if a sample of strontium-90 has a mass of 24 milligrams, find an expression for the mass m of t that remains after t years. So you're coming up with an exponential model for this situation. And I'm going to show you a way you can get to that. So I'm going to start out, in the end we want m of t, so we want an actual function. I'm going to start out with specific values. So I'm going to start out with m of 0. And m is the mass. So m of 0 would be the initial mass. And we know the initial mass is 24 milligrams. So m of 0 is 24. Okay, then I was told that the half-life is 25 years. So that means m of 25, after 25 years, my mass is going to be half of this. Now I know half of 24 is 12. Instead of writing 12, I'm going to write half times 24. So m of 25 is half of 24. Then, after another 25 years, so m of 50, my mass will be cut in half again. So my mass will be half of 24. Okay, now I could also write this as 24. I'm going to kind of switch things around. I could write it as 24 times 1/2 squared. Okay, then if I go another 25 years, so the mass after 75 years will be half of that again. It'll be half of half of half of 24, or 24 times 1/2 to the third. Okay, that's going to keep going. So then, if I'm trying to write t. This is kind of getting me to the form of my exponential function, because this one too I could switch around. This is like 24 times 1/2 to the first. So what do these exponents really mean? The what? The exponent is the number of half-lives. So like this 3 here, because it's been 75 years, the 3 means it's the third half-life. So the exponent is really the number of half-lives. And how would you calculate the number of half-lives? Kyle? Oh, okay. How would you calculate the number of half-lives, Ben? The years divided by 25. So this one, this 3 specifically, is 3 because 75 divided by the half-life of 25 years, that's 3. So the number of years, that's our variable. The 25, the half-life, that doesn't change. So this means our exponent is going to be t over 25. So m of t is 24 times 1/2 to the t over 25 power. And that would be an exponential decay model for the mass of strontium-90 in that situation. Okay, and that's a way to get there just by finding specific values and using the half-lives to get you to what that model should be. Questions on that? You might see this written a different way if you are working on the practice out of the book and you're checking answers in the back. They might write it this way. You might see m of t equals 24 times, and then instead of a base of 1/2, they might put a base of 2 with then a negative exponent. Okay, that means the same thing. Okay, and then part B. So now this is using the model we came up with. Find the mass remaining after 40 years, correct the nearest to milligram. So we know we would be finding m of 40. We're rounding to the nearest milligram. So I do second mode for quit to get back to my home screen. So 24 times, in parentheses, 1/2 or 0.5 raised to the power of, in parentheses, 40 divided by 25. I would make sure on whatever calculator you have, because I know you all have different ones, make sure you can type this in and get the right answer, because that's part of it too, is just understanding with parentheses and everything how to type things in. So it should be 7.917 and so on. So to the nearest milligram would be 8. But make sure you can get that and you're not getting something crazy. So this would be about 8 milligrams. The next question, though, it says use a graphing device to graph m of t and use the graph to estimate the time required for the mass to be reduced to 5 milligrams. All right, so what this means, if you were to set up an equation, the mass is 5, you're looking for t. So if I were to substitute this in here, I'm substituting it in for m of t, I would have 5 equals 24 times 1/2 to the t over 25. Now, could you solve this without graphing? Maybe, depending on how much you remember from pre-calc. Okay, is it possible to solve it? Yes. But you may or may not remember how to do that. We will formally review that, but if you remember, you certainly could do that. Otherwise, I just want to remind you, if you are allowed to use a calculator, you can solve this by graphing. So I could graph my m of t function, I'll call that y1, and then I can also graph the constant function y2. see where they intersect, and that's my solution. Bless you. So if we do that, the 24 times 1/2 to the power of x divided by 25. Oops, I did times. And then I'm also going to graph 5. I'm going to go back to my standard window first, because the window I had would not, or was all mixed up. I had just done zoom box. Okay, so clearly standard window is not great. I can't even see the exponential function. I just see the constant function 5. So I'm going to change, I'm not going to change my y values, I'm going to change my x. So I could probably now change my x min to positive 10, because my x max is already positive 10 and I couldn't even see it, and then extend my x max out to, I don't know where it's going to be, so I'll just do 50. And then I'll hit graph. I'm not going to change the y's. I could have changed the y's. I could have made it so that I wouldn't hit y equals 0. Okay, so now I can see both, but I still am not seeing where they intersect. It's greater than 50. So I'm going to go back to my window, change my x min to 50. I'll change this to, I'll go to 80. Okay, and what I want you to realize, the reason I'm taking time to show you guys this is I'm showing you how I think through using the calculator. So I hear a lot, just because I know working with a calculator, it's not always efficient. It's not always, you know, I hit this and I'm going to get this magical graph that I really, really like every single time. So you have to play around with it. I do too. There isn't a shortcut unless you're using what you know about the functions to play around with the window. There isn't necessarily a shortcut to find what you're looking for. I play around with it as well. Yeah. You had an error. Do you have, what does your error message say? Okay, I'll look at your window. I'd make sure like your min is smaller than your max for both x and y, but then I'll look at what you have to. So then when you can see they intersect, you're just doing the second trace, option 5 for intersect. I'm just going to move my cursor so it's closer to where they intersect, not exactly on it. But then I can see they intersect at approximately 56.576. So T would be approximately 56.576, and that's in years. So it would take approximately 57 and a half years for it to be reduced to 5 milligrams. And then if you did try solving that without graphing, if you tried solving that using logs, see if you got the right answer. Okay, we will review that if you don't remember how to do that. We haven't reviewed it yet. You figured it, okay.